Hello, everyone. Today we're going to be talking about all of the variables we need to describe the stream compositions when we're talking about process flow diagrams. So last time we introduced the idea of process diagrams and how we can use them to perfectly describe an industrial process on the large scale process. So in order to do that, we need a lot more information than we presented last time. So specifically, you're going to want to include uh, complete descriptions of the apparatus used to carry out each of our unit processes and operations. So if this is a reactor, you're going to need to describe what kind of reactor, type, and size. But we're also going to need the same sort of information for all of our various filters, uh, heat exchangers, and the like. But more than that, we also need to make sure we have a complete description of the chemical streams that are involved, because each one of those unit operations and processes is going to generate at least one stream. And what we need to do is, first of all, think about what's going to constitute a complete description of a chemical stream. So we can do this by essentially going back to our general and physical chemistry and think about what variables are going to be required for a complete description of a system. And so, since most of these are a mixture, that means we need to include the composition of the system, the size, which is going to be a volume, or flow, if it's a rate. So this is going to be a flow rate, so volume per time being pumped through, but also things like pressure and temperature. And when we put all of these variables together, that should constitute a complete description of the system. So first thing we're going to really want to focus in on is the description of the composition of these systems. So we're going to need to know what chemicals are present and their relative abundance. And as you know from all your other courses, there is a lot of methods we can use to describe this. However, there is going to be two major descriptions that are typically used in industrial chemistry, though others are definitely present. The first major one is going to be mass fraction. So again, this is going to be the mass of the component I that I care about over the total mass of the system. And one of the reasons why this one is so popular is that it's the easiest to measure. Because if I go ahead and filter out the system or put it through some form of separator, I can mass out each of my individual components, and I can quickly take a total measure of the mass entering the system. As well as I can just tell you to add 10 grams of salt and 20 grams of water. So this is going to be the easiest one for on-the-ground chemists to make use of, is because mass is really easy to measure. However, as chemists, we tend to prefer things like mole fractions. So this is going to be the mole of component I over the total number of moles. And this one is really important to know, as this is the one that dictates chemistry. Because if I'm dealing with a reaction, reactions tend to care much less about mass and much more about molar ratios. Now, it is worth noting that I'm not going to spend too much time on percent volume, though this is also another popular one in industrial chemistry, especially when dealing with gases or any of the parts per system. Again, mostly because these are confusing, because no one ever tells you whether it's in a volume, mass, or molar ratio, and partially because it will follow many of the same rules as the other three. So one of the most important things we need to be able to do is to move smoothly in between our mass and mole fractions, as it is not as very common for a chemical process, an industrial process, to use both descriptions at different points along the way. And as I said, they'll often use mass because it's more convenient, but as soon as you do a chemical reaction, you need to be able to transition into a molar ratio. So most of you are fairly familiar with the process, but I want to walk you through some tricks that industrial chemists use that make it a little bit different. So let's say I've got I have a combustion stream. So I do a combustion reaction, and then out on the tailpipe, I get a nice mixture of mostly nitrogen, because that's the atmosphere that went in, a little bit of unreacted O2, but mostly a mixture of CO2 and CO. Worth noting that the higher fraction of CO denotes that I did not put enough oxygen into my input stream, but we'll get into that later. So our first question is, how can I go ahead and turn these mass fractions, which I may have measured, into mole fractions, which is what I really care about from a chemical perspective, as well as they will be related to the relative pressures of each, partial pressures of each of the components, according to the ideal gas law. So the first trick that industrial chemists tend to use is what's called a basis, which is I artificially set the total, I either artificially set the mass of one of the components or the total mass of the system, and then do everything else through ratios. So when I'm dealing with mass fractions, one of the easiest things to do is to set my basis or total mass to say 100. In this case, 100 grams, which then means that I'm going to have 63 grams of nitrogen, 4 grams of oxygen, 16 grams of CO2, CO, and 17 of CO2. Whether or not I have these actual masses doesn't matter, because this is just going to be a tool on my way to mole fractions. Because once I have the masses, I can go ahead and use my molecular weights to turn these into moles. So then I have the moles of each of the individual components, and this will also give me the total number of moles. So it turns out that a mass basis of 100 grams ends up as a mole basis of 3.3. So one of the temptations when you're trying to convert mass fractions to mole fractions is to only convert one component. One of the big things you have to watch out for is if you're going to convert one component, you actually need to convert all of your components just so you can get this total number of moles, because once I have the individual moles and total moles, congratulations, simple division gets me mole fractions. And there's occasionally some surprises. For example, oxygen had a relative steady amount of mole fraction, and so did CO. But our lighter component, so our lightest component here is nitrogen, had its mole fraction go up significantly, while our heaviest fraction, CO2, had its mole fraction go down substantially. So there can be some occasional surprises when you're converting from one basis to another. So once we know what's present in the chemical stream, we still need to know how our chemicals are going to move in between unit processes and operations. And it's worth noting that we tend to proceed in one of three major bases. The first one is going to be called a batch reaction. So this is what we're usually doing in most chem labs, where all of my chemicals move between systems, in between my unit operations and processes as big lump sums. So I pour out my product from one reaction or one heating unit into the next unit all at once. So you can think of this as I put my mass in, I wait for the reaction or the cooling or the size aggregation to take place, and then I move my whole mass out. Worth noting, these masses may end up changing along the ways. And then we have continuous, which is I have a constant flow rate in and a constant flow rate out. So most modern processes tend to move more in these continuous bases. So I'm going to have steady flow rates in and out, and the process occurs at the same rate all the time. However, these two systems end up being rather easy to solve. Unfortunately, a lot of processes go in what's called a semi-batch process, which can be literally anything in between. So I put in a big mass in, and then I have a steady flow rate out. Or I have a steady flow rate in into my process, but I take out my material as my product as one big mass. Or I may be putting a constant flow rate in and occasionally taking out product. So semi-batch is essentially the fudge phrase for things that don't behave nicely. So we're going to mostly, since this is a short synopsis class, focus in on the two simpler systems of batch and continuous processes. So my batch processes themselves tend to be categorized in one of two major ways. So the first is going to be in terms of the total quantity of chemical being processed. So this would be the total mass in and the total mass out. And then the individual components are given by fractional composition. The other alternative is that instead of caring about the total mass, I'll give you the mass or the moles of each of the individual components. And on top of that, I can also further categorize my system based on one of three different major types of units. So in terms of the volume, either total or component, the mass, total or component, or the moles, total or component. One of the things that you should watch out is that chemical engineers will occasionally refer to moles as gram moles. So this is the amount of substance whose mass equals its molecular weight in grams. More or less, this is the same thing as moles. But one of the other units they tend to use, and this is a little bit messy, is kilogram moles, which is the amount of substance whose mass equals its weight in kilograms. This is the same thing as a kilomole. So watch out. There might be some weird units that come up occasionally, just so you're aware. And one of the important things is, just like we go through in basic chemistry, it's important to be able to know how to be able to switch in between these units, not just in terms of volume, mass, and moles, but also in terms of percentage components, the components in a percentage system, and the components in a amount system, which is a lot of different conversions to watch out for. Similarly, we can characterize batch processes in a similar fashion. So either in terms of the total flow rate in and the fractions of each component, or the flow rate of each fraction. So for example, I may be ending up describing my system in terms of the total volume flow rate in liters per second, or if I have two components, say oxygen and nitrogen, the flow rates of each of those two individual components. However, we also have mass flow rates and molar flow rates. One of the big things you should note, and I will occasionally biff on this, is that if you see a V dot, this indicates that it's going to be a volume flow. Similarly, when you see a dot above the M and N, this indicates mass and molar flow rates respectively. Now, one of the things you should watch out for when you're putting terms into flows is that there can be a big variety of choices in terms of the unit of time used. And this can often be a little bit troublesome. So make sure, whether it's in seconds, days, hours, minutes, all are fairly common units. However, this just helped us describe the composition of our systems. Turns out we also need to make sure we refer to the pressure of our system, because it turns out that knowing the pressure can be rather important, as it can help us avoid catastrophic disasters. What you see over here on the right is a heat exchanger that got overly pressurized with ammonia. Yep, that ended up badly. Thankfully, nobody was hurt in that one, but it did cause quite a bit of damage to the facility. And remember, for gases, as long as we're operating near the ideal conditions, we can use the ideal gas law to help convert in between essentially molar flow rates and pressure temperature ratios. Again, this allows us for smooth conversions in between volumes and moles of the substance, or volume and molar flow rates. But in order to do that, we need to know pressure and temperature. And again, watch out, as there are more pressure units than you can shake a stick at, and industrial chemists love all of them, including, yes, PSI and millimeters of mercury. Both are old favorites. Similarly, it's also very important that we make sure we know the temperature of the system. And again, one of the major reasons is that pressure and density tend to be temperature dependent properties. So in order to have smooth conversions in between volume and mass, or volume and moles, it's often very important that we know the temperature of the system. Furthermore, along with pressure, temperature is really important in identifying the phase of the system, and different phases are going to behave very differently, and we're going to have to build very different systems to contain those phases. Furthermore, almost every thermodynamic and kinetic property are going to be temperature dependent. Yes, that is our rate constants, which is going to dictate things like percent yield, and our rate constants, which is going to determine a lot of things such as the rate of reaction. So if you need to make sure you slow down your reaction so it doesn't run away on you, temperature is going to be a major control. So always make sure you try and specify the temperature of the system, as it turns out that a large portion of industrial chemistry is going to revolve around careful changes of the temperature of the system. And indeed, that's where a lot of the money goes, is into heat transfers. Furthermore, one of the things you should always watch out for is chemical stabilities, because every chemical you'll ever encounter is going to have a stable temperature regime and an unstable temperature regime. This is most important to watch out for in biological systems, as these tend to degrade at what in industrial chemistry would be considered relatively mild temperatures. They'll degrade at what, 35 degrees C? That's just unallowable. Real chemistry happens at about 500. So that's one of the major reasons you should watch out for temperature. Hopefully, most of this is going to be a review. Next week, we're going to go ahead and start on into the real bread and butter of industrial chemistry, and that's mass balance. Till then, take care.